You can apply the law of conservation of momentum to collisions. Take a system made up of just two particles. If you play pool, say, the cue ball and the 8-ball. Now the net momentum before the cue ball and the 8-ball collide is going to be equal to their total momentum after the collision. To be clear, I am adding up the momenta of the two balls before the collision and saying that it is equal to the sum of the two balls' momenta after the collision. Remember that net means sum of. I'll let our guest stars explain further.
Let's say we have two objects in the system, a steel ball and a styrofoam float.
At first, the styrofoam float is moving.
The steel ball is not.
We're going to use a beaker and a test tube to represent the conservation of momentum with this system. The diameter of the beaker represents the steel ball's mass, and the diameter of the test tube represents the mass of the styrofoam float. Obviously, the styrofoam float has a much smaller mass. The steel ball has a larger mass. But the height of the column of liquid in the test tube represents the object's speed. The styrofoam float has some speed. The steel ball at first has no speed.
We have a collision between the styrofoam float and the steel ball. At first, the styrofoam float is moving very fast, but upon collision, it transfers some of its momentum to the steel ball.
So now the speed of the steel ball is very small, but the speed of the styrofoam float is down to 0. That's the conservation of momentum.
This equation is really quite powerful because you can use it to tell the future. Did you know that some physicists actually used to believe that they would be able to predict the entire future and the entire past from a single moment if they only had enough information? If you know the total momentum of a system before a collision, you can actually predict the speed of an object after a collision. But it is a little more complicated than that. See, there are two types of collisions. There are elastic collisions and inelastic collisions. And in an elastic collision, even if the objects temporarily change shape, they spring back to their original shape after the collision, just like an elastic rubber band springs back to its original shape after you stretch it. In other words, the objects don't change shape and they don't stick together. Here we have three different examples of elastic collisions. Notice that in each example, the balls do not stick together and they retain their shape throughout. In example A, the green ball is initially moving, the yellow ball is motionless. They collide, and the green ball transfers all of its momentum to the yellow ball. After the collision, the green ball is motionless and the yellow ball is moving. In example B, initially the green ball and the yellow ball are moving towards each other. There is a collision, and after the collision, the balls both move away from each other in the direction that is opposite, right? Opposite to their initial directions of motion. Finally, in example C, both the green ball and the yellow ball are moving in the same direction to the right. The green ball is moving a little bit faster, though, than the yellow ball. After the collision, the green ball is moving with the speed of the yellow ball, and the yellow ball has the speed now of the green ball before the collision. If you knew the masses of these balls, you could actually predict their speeds after the collisions. Now let's move on to inelastic collisions. In an inelastic collision, objects do change shape after the collision. In simple terms, they stick together. Again, you can use the law of conservation of momentum to make predictions about the object's motion after the collision. In this case, I know that the objects will be moving at a speed of 5 meters a second after the collision if before the collision one has a speed of 0 and the other has a speed of 10. Now, how do I know that? Well, here we go. So let's say both cars have the same mass, m, and initially one car is moving at 10 meters a second and the other car is at rest. That means that the net momentum before the collision is just m times 10, right? The second car isn't moving, so its momentum is 0. So the net momentum, the total sum of the two cars' momentum, is simply m times 10. Now, by the law of the conservation of momentum, the net momentum before the collision equals the net momentum after the collision. And the momentum after the collision is equal to the total mass of the two cars times their speed, which is what I want to find out. I know that it equals the total mass of the two cars times their speed because the two cars stick together, and the first car's mass is equal to m, and the second car's mass is equal to m, and m plus m equals 2m. Now, I am almost there. I have m on both sides of the equation. So that means I can just cancel it out from both sides of the equation. In other words, I'm just dividing both sides of the equation by m. And that means m divided by m equals 1. 2 times 1 is just 2. And 1 times 10 is just 10. And so I'm basically there. All I'm left with is 10 equals 2 times v. And 2 times 5 is equal to 10. In other words, v equals 5 meters per second. Sweet. It's your turn, my young physicists. Freight car A is moving toward identical freight car B that is at rest. When they collide, both freight cars couple together. They have an inelastic collision. They stick together. Compared with the initial speed of freight car A, the speed of the coupled freight cars is what? The same? Half? Twice? None of the above. Pause the video now and select your answer. The correct answer was B, half. And here's why. After the collision, the mass of the moving freight cars has doubled. I'll leave it up to you to determine why their speed is half the initial velocity of freight car A. And that brings us to the end of collisions and the end of this unit. Congratulations.